My name is Nicholas Pepe, and my group decided to do combustion chemistry as our overall concept. In the slides to follow, we will each discuss our specific topics in greater detail, but for now, I will just introduce our topics. I chose to do firework chemistry, Mike did bomb combustion, Jeffrey did rocket fuel combustion, and Jet did fulgurite formation. So as I said, our group topic is combustion. Combustion is basically a chemical reaction that has a compound or mixture reacting with an oxidant to form energy. Usually that energy is given off as heat and light of some sort. A common example that is considered in most chemistry classes is a lighted match. When friction is applied to the chemicals on the match, there is more heat forming than the amount that can escape into the air, so a flame is produced. For my specific topic, I chose to do firework chemistry. Fireworks can be broken down to three main aspects: the physical design, the chemistry behind the explosion, and the chemistry behind the colors. The physical design is quite simple. If you look at the picture on the left, this is the inside of a standard firework. First, there's a fuse that leads up to the black powder propellant, which is what makes the firework fly into the sky. While this is happening, the time fuse keeps burning, and once it is in the air, at the desired height, the flame will reach the black powder bursting charge and the effect pellets, and it will explode. Usually in fireworks shows, the fireworks have different length time fuses, which allows the fireworks to explode at different heights and not all in the same spot. The black powder that allows the firework to propel into the sky and also explode is made of potassium nitrate, sulfur, and charcoal. Each of these are in their solid state, which means they have a very defined shape and volume, and that they can form defined crystal lattices. Potassium nitrate, once heated, undergoes a rhombic to trigonal transition. This makes it more reactive and easier to ignite. Sulfur becomes increasingly less stable when the temperature rises, so much that there is a decreased porosity. This makes sulfur so uniquely reactive compared to its competitors. Charcoal is the crucial element of this mixture that provides key characteristics for combustion. This is because when it is in finely divided forms, there are a lot of surfaces that are only presented with partially saturated attractive forces. This means it can absorb large amounts of gases and vapors. The last aspect to explain in fireworks is where the color comes from. It is a common concept in chemistry that burning different metal salts produces different colors. Each element will burn a different color because of their unique number of electrons and how they react to each other in the shells outside of the nucleus. Some examples are shown in the chart on the left. As you can see, strontium salts burn to make red, barium salts burn to make green, and copper salts burn to make blue.
Hi, my name is Michael Conrad, and for my specific topic of combustion, I wanted to relate the idea of combustion as best as I could to information we've learned about in class. The conclusion I came to from this was using the bomb calorimeter that we had talked about in class, which we also did labs on in our lab class. And the basis of how the calorimeter connects to combustion is how the energy is released by the combustion and heat flow. A bomb calorimeter is a constant volume calorimeter that is used to measure the heat of combustion of a reaction. They have to be able to withstand the extreme pressure as the reaction is being measured. A type of electrical energy is used to ignite the fuel, which will heat up the air that surrounds it. This air then expands and escapes through a tube that goes out of the calorimeter. While it leaves the tube, it heats up the water as well because of the energy. The change in temperature of the water allows us to then calculate the calorie content. The two journal articles I studied included two specific experiments that used calorimetry and combustion. One used tritium and the other used biodiesel as a measurement to further experimentation on the two. The tritium experiment really closed in on how the calorimeter could be used to see the maximum heat of the combustion reaction occurring. The biodiesel one was very interesting because biodiesel is currently a popular topic in the field of chemistry. Over a 3-week period, students synthesized biodiesel, measured its heat of combustion, density, and cloud point, then compared these properties to conventional petroleum diesel. Heats of bomb combustion were measured in a common laboratory bomb calorimeter. This journal article by Akers and others really leaned on the idea of thermodynamics and bomb calorimetry. For example, a quote made by Akers about the connection states, "The thermodynamics of bomb calorimeters are modeled using a lumped heat transfer analysis in which heat is released in a pressure vessel bomb and burst in a stirred water bath that is surrounded by a static airspace bounded by an insulated jacket. Bomb calorimetry is a helpful tool to understanding complete combustion."
So for my part of the presentation, I'll be going over rocket fuel combustion, and I'll be comparing liquid propellant and solid propellant first. Now, in solid propellants, you have the fuel and oxidizer, as you can see here, mixed together already. And when the source of heat is ignited, the reaction continues until there is no more fuel left to burn. Whereas in a liquid propellant, the fuel and oxidizer are separated. And this allows for the rocket to control the amount of thrust given by controlling the flow of the liquid and oxidizer using these pumps. Now, while you may have control of thrust with the liquid propellant, you also have less thrust due to how mass is taken up by the pumps and the fuel and oxidizer containers. And mass is important for combustion, as you can see in this equation provided here by the Glenn Research Center, which shows how thrust is equal to mass times volume plus the exit pressure minus total pressure multiplied by the area. And this equation also allows us to see how combustion reacts is related to the ideal gas law and pressure and temperature, because as you can see here, pressure is directly proportional to temperature. So if you increase the pressure, that means the temperature can also increase and the volume would decrease. And as you can see in this equation here, T2 is equal to T1 plus heat over specific heat times velocity. We can see how temperature and heat are be related together using the first law of thermodynamics. And now I'll give it over to Jet Tinnick, who's going to talk about fulgurites.
Thank you, Jeff. Hello, I am Jet Tinnick, and today I will be going over fulgurite formation. Fulgurites are an artistic and chemical wonder of nature. Today I will be going over the combustion chemistry behind fulgurites, as well as its use as a geological substitute in a science experiment. Also known as petrified lightning, scientists believe that this substance is created under longer duration lightning strikes due to the lower amount of amperes that is put into the substance in regards to regular lightning strikes. Granular ground is required for this substance to be formed because of the moisture and air inside of the minerals. And when lightning strikes it, it causes the air and moisture to expand rapidly, also heating up the outside substance into a molten glass. The cool atmosphere then rapidly cools the substance, creating the fulgurite as we know today. In the science experiment, researchers asserted that the conditions that a fulgurite was under, the intense heat and pressure, could parallel that of shock metamorphism, what rocks endure over thousands and thousands of years. So they compared different fulgurites and their redox changes, and they concluded that the physical state actually had something to do with the outcome of the substance after being put through the intense heat and pressure. We just wanted to go over what combustion was. Combustion was when a compound and an oxidant come together and create some form of energy. And we hope that you learned a lot about combustion today. We were very fascinated with what we found, and we hope that you enjoyed the presentation. Here are our references, and thank you for your time.